How are you doing today? This is Mike Johnston here, and in this video we are going to discuss the way that numbers are qualified, the way that we qualify different numbers, and how, and actually the different meaning behind several of our numbers. So I know that as I was growing up, that I was heard, especially in math courses, I heard terms like integers, I heard terms like real numbers, I heard terms like imaginary numbers, and many times I always found that very confusing. So in this video, we're going to go through the way that numbers are categorized and qualified. So if we look at all numbers, I like to work this through very similarly to a process flow diagram. So I know that if I have any number, that I can break this categorization up into two different, in essence, dichotomies. So I can break this up into two different categories initially. There's going to be real numbers, which we abbreviate with this funny looking R with two vertical lines, and then there are imaginary numbers. So any value can be broken down into a real value or an imaginary value. So what I like to do is I like to sort of go ahead and describe and define these, and I'll do this over here to my right. So let's go ahead and try to define these to our right here. So if we were to look at a real number, if I wanted to define a real number, I'm going to do so using both abbreviation and me writing out longhand. A real number. A real number, just a very easy definition, is any value that can be found on the real number line. Any value that can be found on a real number line. So I'll go through and I'll shoot some examples to you. Some examples. 3, for example, is a great real number. We're going to learn later on that 3 is also an integer. It's also rational. Also, -3. That is another example of a real number. 0.016. So decimals are real numbers. No matter how small or large the decimals are, whether they're positive or negative, they're also real numbers. If we look at any value of pi or any multiple of pi, these are also real numbers. Even though they're not the nicest or prettiest values, they are still considered real. We're going to learn later on, they're irrational, but right now they are considered real values. We also can experience real values that are fractions, or negative fractions. Fractions and negative fractions are also examples of real numbers. And then lastly, I know this one tends to be more confusing to a lot of people, but 0 is also considered a real number. So 0 is also considered a real number. So if we were to look at these real numbers, especially in most of our classes of applied math, that most of our classes are going to be categorizing using real numbers. We mostly use real numbers. Very rarely are we going to work with imaginary numbers. So imaginary numbers are a little bit different. So if a real number is any value that we can find on the real number line, then an imaginary number or imaginary numbers are any values that cannot be found on the real number line. So the best example that I can give of an imaginary value is going to be that value of I, where I is equal to the square root of -1. So whenever we have that radical, and there is a negative value, and our index of that radical is even, we know that we're going to have an imaginary value. So some more examples that may not be presented in terms of I, you might see something like square root of -5. Square root of -5 is considered imaginary. If we were to look at another example, we may say the fourth root of -8. So even though this is not a square root, this is the fourth root because the index here is a value of 4, and we write this value, this is the index. the index is a value of 4, which is an even value, which really is asking the question, what times itself 4 times gives you a value of -8, and there's no value that you can ever multiply through an even amount of times that will ever give you a negative. So let's go ahead and let's analyze maybe one that is not imaginary. So this guy, even though he has a negative underneath the radical, his index is a value of 3. And that value is odd. And this actually reduces down to a value of, not reduces, but actually simplifies through to a value of -2. And -2 is actually okay. So this circumstance actually here, this guy is a real value. He is real. He is not imaginary. So when we go through and look at such, we realize that initially all values can be broken down into real or imaginary categories. So now let us go back to our process flow diagram. Let us go back to our process flow diagram here, and we recognize that if a number is qualified as imaginary, I put a little star here, a little asterisk, representing that it will no longer be subqualified. There's no other qualifications. Once a number is imaginary, it's considered imaginary. However, if a number is real, this brings us through to our next dichotomy. So our next dichotomy is going to be broken down by analyzing our group of real numbers, which I'm going to do so in blue. And we see that that's a little bit patriotic, actually. So if we look at real numbers can be broken down further. And real numbers can be broken down into rational values, rational, and then irrational values. So any real number must be one of these two. It must be one or the other. If you have a real value, it must be irrational or rational. If you have a number, it must be real or imaginary. So even though I didn't write that here, let me just go through and write that in there. If we have a number, it must be either or. It must be either or. So let's go ahead now and define the terms ratio. And I'm doing this pretty generally. We're not really getting into the definition of all numbers, but something just to help you understand how to identify a real and imaginary number, but also a rational versus irrational. So let's go through and now let's go ahead and identify the difference between a rational value and an irrational value. So if I were to look at the term ratio, I realize, I'm sorry, the term rational, I sort of gave it away there. The root word of the term rational is in fact ratio. And when I think of a ratio, I think of a fraction. And this is a very generalized way to define this, but a rational value is any value that can be written as a fraction. So any value that can be written as a fraction. So let's go through and give some examples. So we definitely can see that includes both positive and negative fractions. We realize that decimals can be converted to fractions, right? Because we just say this is going to be the tens, hundred, thousandths, 10,000ths decimal units. So this will be 168 10,000ths. A value of 0 can be written as a fraction. These integers, 4 and -11, for example, they can be written as, those are rational values as well. So these are all rational values. They can be written as fractions. We can find some way to convert them to fractions. So that begs the question of an irrational value. And the nice thing is that when I work with irrational values, every time I place that abbreviated portion of the word, not abbreviated, when I place that prefix in front of the term rational, I get ir. Ir is going to negate this. So this will be any value that we cannot write as a fraction. So that question sort of says, okay, you know what? How can we not write a value as a fraction? So if we look at this, I will give us some of our better representative irrational values, and those are usually involving the term of pi or any multiple of pi. So pi exists infinitely long in terms of its decimal units. It never ends. It's non-terminating. It exists through infinity. That any multiple of pi will also never ever stop. There are actually scientists around the world, mathematicians all around the world that calculate pi to infinitely long decimal places. I don't personally understand the goal of doing that, but again, it proves the fact that it is an infinitely, it is a value that never ends. It has an infinite value. And since it can never terminate, we can never write that as a fraction. So that's why we call this irrational. We are also going to learn that that is not the only irrational value, but any square root, and we'll say just square roots right now. This will expand later on when we take high level courses. But any square root of a non-perfect square. So I'll even write that. I'll write that in here. So as a little asterisk, any square root of a non-perfect square. So square root of 7, for example, square root of 11, negative square root of 5. These are all considered irrational values. As you advance through mathematics, you're going to realize there are also a couple more types of irrational values that are not specific to square roots, but you will also realize later on that they are going to be expanding upon third, fourth, fifth, sixth, and seventh roots. So anytime you have a root that does not simplify to an integer value, that value will be irrational. So just in this video, to keep it at approximately 10 to 12 minutes, I don't want to continue on with this process flow chart, but I want you to understand that in this initial description that we can break down our numbers. Our numbers can be broken down into imaginary and then real numbers, and then if the number is real, that it can be broken down into irrational and rational values. And just as one last note before we end this video and go on to the next one, that if a value is considered irrational, it can no longer be further qualified. So once a number is irrational, then that way we know it is the most qualified it could possibly be.